Now that we've talked about simplifying in the most basic sense, we can look at, some more complicated expressions. Just because they look complicated doesn't mean that they are, or doesn't mean that we need to make them complicated. So if I want you to simplify the fifth root of 32, a to the 40th, b to the 65th, c to the 15th, you need to look for something, an expression that can be multiplied 5 times to get this. And so I go through piece by piece. Is there something I can multiply 5 times to get 32? Yes, that number is 2. And you really should know another good piece of knowledge to have is the powers of 2. 2 to the first, 2. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32, etc., etc. So knowing your powers of 2 is really, it's helpful. The fifth root of 32 then is 2. The fifth root of a to the 40th. So is there something I could multiply 5 times to get a to the 40th? Yes. 40 divided by 5. This 40 is divisible by 5, so I know that it exists. And what it is what I get when I do, or has a power of 40 divided by 5, that is 8. So the fifth root of a to the 40th is a to the 8th. The fifth root of b to the 65th, 65 divided by 5 is 13. So this is b to the 13th. And the fifth root of c to the 15th, 15 divided by 5 is 3. So this is c to the third. And you can always verify, if you multiply this 5 times, you will get 32, a to the 40th, b to the 65th, c to the third. So like I said, just because it looks complicated, it doesn't have to be. And that's always the case when, these factors underneath are, so since this is a 5, these are fifth powers. When we get into some expressions, that's not always going to be the case. And it is examples like this or expressions like this that get a little bit stickier. So if I'm asking, or if I'm trying to simplify this expression, the first thing I always do is say, okay, looking at everything underneath, is there something I can multiply 3 times to get 16? Is there something I can multiply 3 times to get x to the 4th? Is there something I can multiply 3 times to get y to the 6th? That one's a yes, but the rest would be a no. Okay? And if ever when you're simplifying, if ever there is a no, if ever it is there a cube, is there a number I can multiply 3 times to get any one of these things, if any of those answers is no, then we can't do what we've been doing. Okay? That expression can't be simplified to just some nice, pretty, non-radical expression. But if any of these factors are divisible by a perfect cube, we can do some simplification. Okay? We'll talk about recognizing what that means. So if it is not the case that every factor in the radicand is a perfect cube, but at least one is divisible by a perfect cube, then it can be simplified. So this is your overall, it can be simplified if this is the case. Okay? If at least one of these is divisible by a perfect cube, we will be able to simplify even if it is not the case that every factor is a perfect cube. And in order to do our simplification, we're going to have to employ the product rule of radicals that says that for any root n, as long as the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is the nth root of the product of those radicand ab. Okay? So let's look at doing this simplification. So when I look at this, I know it can be simplified, and the easiest way, without even thinking about this number 16, if any of these powers are greater than or equal to this number here, you know it can be simplified. Okay? So basically, if this number is divisible by a perfect cube, or if any of these powers are greater than or equal to the index, we know that the expression can be simplified. Let's write that down. So we know we can simplify if the number, if there is a number, is divisible by a perfect cube or if any of the exponents are greater than or equal to the index. Okay, and remember this number here, that is our index. So we know it can be simplified. Okay, and so when we are trying to simplify, when we cannot just evaluate that radical expression, what we will do is use that product rule. So we are going to take the expression above and we are going to rewrite it as the product of two cubed roots. Cubed root here, cubed roots here. Okay, and how I'm going to do that is I have three conditions that need to be met for me to do this successfully. The first condition is every factor, everything that I put in here is going to be a perfect cube. Okay? Everything must be a perfect cube. Also, it will have to be that none of these are perfect cubes. And also, I guess maybe a fourth condition, our powers need to be smaller than 3. Okay, whatever the index is. So if this was a 4, then our powers would have to be smaller than 4, etc., etc. So, and the last thing is, whatever I put underneath, it has to be that the radicands, that's an R, I'll rewrite that, the radicands must multiply to our original radicand. So when we multiply these two together, the product of these two has to be 16 x to the 4th, y to the 6th, z to the 10th. Okay? So when you're working on simplifying radical expressions, all of these things have to come into play. Okay? So these two expressions have to multiply to this. So I know that I'm only working with factors of this expression here. So when I start, I'm going to start with that 16, and I'm going to think about what numbers divide into 16, or the factors of 16. So if I think about the factors of 16, I know I can multiply 1 by 16. I know I can multiply 2 by 8. And the only other factor of 16 is 4. If I multiply 4 by 4, I will get 16. So I'm looking at my factor list. And I know that underneath here, to simplify, I can only do that for the 16 if I can put a number in here that's a perfect cube. So when I look at this list of factors, 1, 2, 4, 8, and 16, 1 is a perfect cube and 8 is a perfect cube. But I always want to use the largest perfect cube factor. And again, cubes because of the index. So 8 is the largest perfect cube that goes into 16, so it is the 8 that I will put here. This times this has to be 16, and so 2 is what goes here. Okay? So none of these numbers are perfect cubes. And you know, we really should say none of these numbers are divisible by perfect cubes. That would be really more accurate for what we're looking at. 2 is not divisible by a perfect cube, so we're good to go there. So that's a perfect cube. That is not, then that's not divisible, and this times this is 16. So my x to the 4th, I know I can simplify because this power is larger than this index. So what I'm going to do is I'm going to break apart my x's because x to the 4th is not a perfect cube, and I'm going to do so in such a way that the expression that I put here is a perfect cube, and that is not divisible. So the power has to be smaller than 3 for that to be the case. So the largest perfect cube factor of x to the 4th is x to the 3rd. And I would multiply this by this to get x to the 4th. So that would be 1x there. Okay? Power is smaller than 3, and that's a perfect cube. So we're good to go there. Y to the 6th is a perfect cube, so I will put that y to the 6th in this expression because I'm always putting perfect cubes there. The only other way that I could deal with this is by putting y to the 3rd, right? These powers have to be divisible by 3 for the expression to be a perfect cube. And if I did y to the 3 here and y to the 3 here, then that number, that 3, is not less than our index, so I can't split my y's. My z to the 10th, so basically I'm thinking, alright, less than 10, what's a number that's divisible by 3? And that would be 9. So z to the 9th is the largest perfect cube factor of z to the 10th, and I would have to multiply z to the 9th by z in order to get z to the 10th. So what we have is this expression where everything underneath this cube root is a perfect cube. So this can be evaluated, and we would have to leave this as it is. So the cubed root of 8, what can I multiply to get 3 times to get 8? That is 2. 3 times to get x to the third, x. 3 times to get y to the sixth, y squared, and 3 times to get z to the ninth, you would multiply z to the third. So the simplified version of this expression is 2x y squared z to the third times the cubed root of 2xz. Okay? So once I've done the split, then I am able to evaluate this, but I'm not able to simplify then any of this. It should always be that what you're left with is powers smaller than your index and a number that's not divisible by a perfect cube underneath. If what you start with is an expression where you don't have all, in this case, perfect cubes. Okay? So let's keep on applying that basic idea. So you should always first start to try to find a rational number. So when you're dealing with numbers, you're looking for some rational number, some real rational number that you can multiply. Here, the index is 2. So I'm looking for something that I can multiply twice to get 40. Try as hard as you might, but that number, there is no number that you can multiply twice to get 40. Okay? So in terms of evaluation, I cannot just find a number. I can't just find some number I multiply twice to get 40, some rational number. So that's this first part. Is this a perfect square? No. Okay? This is not a perfect square because there does not exist a number I can multiply twice to get 40. Then I say, well, okay, it's not a perfect square, so I cannot just evaluate, but can I simplify? Is this radicand divisible by a perfect square? So if I go through and I think about all of the factors of 40, factors of 40, I can multiply 1 by 40, I can multiply 2 by 20, I can multiply 4 by 10, and I can multiply 5 by 8. And that is a complete list of the factors of 40. And so looking at the factors of this number, is 40 divisible by a perfect cube? Are any of these factors, I'm sorry, not cube, a perfect square. Are any of these factors perfect squares? And you always want to, if it is divisible by a perfect square, you want to find the largest perfect square that goes into that number. So I'll start at the top end and work my way back. Is 40 a perfect square? And you can look at the perfect square list that we created at the beginning of the first chapter 9 video. And you'll see, no, 40 is not, 20 is not, 10 is not, 8 is not, 5 is not, 4 is. So because our 40 is divisible by a perfect square, I can simplify this expression. Okay, so is this radicand divisible by a perfect square? Yes, it is divisible by 4. And so to simplify, anytime it's not a perfect square, but it is divisible, that is the case when we always then split it into 2. Remember, my 3 conditions then are that what I put here must be a perfect square, what I put here, it must be a number that's not divisible by a perfect square. And lastly, the product of these two numbers must be 40. So I found that the perfect square factor of 40 is 4. What do I multiply 4 by to get 40? That number is 10. Just to make sure that I found the largest perfect square, if we think about the numbers that go into 10, or that 10 is divisible by, 1, 2, 5, and 10, 1 is a perfect square, but that doesn't count. So we cannot simplify that anymore. So, and 4 times 10 is 40. So now that we have this separated into the product of 2, now we can evaluate the square root of 4. What can I multiply 2 times to get 4? That number is 2. So the square root of 40 is equivalent to 2 root 10. And for any of you, interested in the notation, please be aware that the square root of 40 and 2 root 10, they are both notations that represent the same irrational number. If you, do some calculations on your calculator, and I'm going to stick with decimals here, I'll show you that if I type, let's see if you can see it, kind of, sorta, the square root, there we go. If I type in the square root of 40 into my calculator, it gives me this 6.32455 da 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 da. And the square root of 40 is actually an irrational number, so that is a decimal number that never ends and never repeats. My calculator, of course, is limited in the display, but I could never actually write that decimal number, right? Decimal part that never ends and never repeats. It would be physically impossible for me to write this decimal number, which is why having notation to represent these irrational numbers is so important. If I type in 2 root 10 into my calculator and evaluate it, you see I get the same decimal number. The square root of 40 and 2 root 10 are both notations for something that I can multiply twice to get 40. And so to go a step further, you'll see if I multiply the square root of 40 by the square root of 40, I do get 40. If I multiply 2 root 10 by 2 root 10, I also get 40. Okay? Square root of 40 and 2 root 10 are both notations that represent real numbers that I can multiply twice to get 40. They both represent the same irrational number. This is the most simplified version of that. Look at another example. Simplify the 5th root of x to the 32nd. So I could simply evaluate if this number is divisible by, when I'm dealing with exponential expressions, if this power is divisible by this number. 32 is not divisible by 5. So I know that I cannot just evaluate. I am going to have to, if it will simplify, I'm going to have to break it into the product of 2 radicans to do that. I know it will simplify because this power is larger than this index. Okay? So when I go to do my split, so I'm going to rewrite this. To simplify, I'm going to rewrite this as the product of 2 fifth roots. Okay, again, what I put here is going to be a perfect fifth power. Okay, and the easiest way to recognize those would be numbers where the exponent's divisible by 5. And what I put here, this cannot be divisible by a fifth power. And in the case of exponents, you know, the easiest way to recognize that is that the power must be less than 5. Okay? And then finally, that last condition is that the product of these has to be x to the 32nd. Okay? These two radicands must multiply to x to the 32nd. Okay? So, and I'm thinking about that, so I'm just trying to think about numbers less than 32 that are divisible by 5, and the closest number less than 32 divisible by 5 is 30. So, x to the 30th, that is a perfect power. If I do 30 plus 2, I'll get 32. So I know this should be x to the second in order for the product of these to be my x to the 32nd. So the fifth root of x to the 30th, I can do that by just dividing 30 by 5, that is 6. So we end up with x to the 6th times the fifth root of x squared. And it's very important when you're writing your simplified expression that you do, if the index is, something other than 2, it has to be there. No index means the square root of x squared, which we know is x, okay? Which is very different than the fifth root of x squared. So be very cautious in that you always put, if you have an index other than 2, you need to make sure that that index gets placed in your final simplified answer. So this is the simplified expression of the fifth root of x to the 32nd. Again, both of these notations represent something that can be multiplied 5 times to get x to the 32nd. But while it may not look to be more simple than that, this is what we call the simplified version of that expression. Okay, one final example before we move on to adding and subtracting. So let's do one last example. So evaluate or simplify the cubed root of 81, a to the 20th, b to the 9th, c to the 8th, d, blah, blah, blah. So, is there something I can multiply 3 times to get 81? And if you look at your list of perfect cubes, you're going to see 81 is not on that list. 81 is on the list of perfect squares. It's not on the list of perfect cubes. I cannot simply evaluate the cube root of 81. I am going to have to now think, well, is 81 divisible by a perfect cube? And I know a to the 20th, b to the 9th, c to the 8th. All of these powers are larger than this, so I know this expression can be simplified even if 81's not divisible by a perfect cube. So without even going there, I know that I am going to have to simplify because at least one of these powers is larger, greater than, or equal to my index. So doing my simplification, so for the 81, let's list some factors of 81 up here. So the factors of 81. I can multiply 1 by 81. 81 is not even, so it is not divisible by 2. It is divisible by 3. I can do 3 times 27. 81 is not divisible by 4, not by 5, not by 6, not by 7, not by 8, but it is divisible by 9. And you can use your calculator if you don't know what 81 is divisible by. And 9 times 9, so I know I can stop because I've got my two factors overlapping or as close as they can be. So 1, 3, 9, 27, 81. These are the only numbers that go into 81. So I will, break this up if any of these numbers is a perfect cube. So if you go back to your list of perfect cubes and you're trying to find the largest, so work your way backwards. Is 81 a perfect cube? No, it is not. Is 27 a perfect cube? Yes, it is on that list. So we will put only, again, when we're doing this, we are only going to put perfect cubes in here. And what we put there, we can't put any number that's divisible by a perfect cube. Okay? None of these can be divisible by a perfect cube. So we found 27 is a perfect cube that goes into 81, and it's important that it has to go into 81 because the product of these have to be 81. So the number that goes here, the number that I multiply 27 by to get 81, that is 3. A to the 20th is not a perfect cube. I cannot find an expression that I multiply 3 times to get a to the 20th. So I know I'm going to have to break apart my a's. So I do that by thinking about, with the variables, you can think about numbers divisible by 3. So less than 20, but divisible by 3, that closest to 20 that's divisible by 3, but less than is 18. So a to the 18th, and I would have to multiply a to the 18th by a to the 2nd to get a to the 20th. B to the 9th is a perfect cube, so it goes here. C to the 8th is not a perfect cube. And this is something that really messes with people. Yes, the number 8 is a perfect cube, but C to the 8th is not. When you're dealing with an exponential expression, it has to be that the power is divisible by 3 for that to be a perfect cube. So C to the 8th is not a perfect cube. The largest perfect cube factor of C to the 8th is C to the 6th. So this is going to be C to the 6th, and we would multiply that by C squared. And D to the 1st, this power is already less than 3, so I know that this is not divisible by a perfect cube. So I will just put my D here. Okay, so just a quick check. When I multiply these, do I get this? Yes. Are all of these perfect cubes? Yes, right? All of these powers are divisible by 3. And is it true that 3 is not divisible by a perfect cube other than 1? Yes. Is it true that all of these powers are less than 3? Yes. So what we did so far is right. Okay? And now that we have it broken apart like this, now we are able to evaluate this cubed root. What can I multiply 3 times to get 27? That is 3. 3 times to get a to the 18th is a to the 6th. 3 times, so we've got 3a to the 6th. The cubed root of b to the 9th is b to the 3rd. The cubed root of c to the 6th is c squared. And then we have times the cubed root of 3a squared c squared d. Right? That remaining part that cannot be simplified. So make sure you have this idea in your head. You're really going to have to, like I said, if you have in your brain, if you can recognize perfect cubes and perfect squares, it's going to make your work a lot easier. And next we will start talking about how to do some operations with these radical expressions. Let me know if you have questions.